Long story short, arrows change your position on the screen. Select inserts a device or wire, or changes the logical nature of an instruction. OK confirms the selection, and delete deletes something. Once you've entered a program, press Escape to back up and save it. And away we go. Returning to our blank program screen, we can now enter our basic program. Press Select. The device inserts contact I1 as a make instruction. If I wanted to make this a break function, I'd have to press Select again. The TECO SG2 PLR indicates a break instruction function with a lowercase. If I wanted to draw a wire, I'd have to press Select again. If I press Select again, I'd be back to a blank device, and if I press Select again, I'd be back to the original terminal input entry of input 1. The up and down arrows, in contrast, change contact function X, Z, Q, Y, M, N, D, T, C, R, G, and back to I. We'll examine these other entries in later lectures. Once you got whatever contact function, right arrow to the contact number. We want input 2, so we're going to increment to 2. Press OK to confirm input 2. The device inserts input 2 as a make instruction and moves us one column to the right. If you dork something up, you can always delete it. Press Select to insert another contact. This device again inserts the default contact I1 as a make instruction. Right arrow to the contact number, increment it to 3. Press OK to confirm I3. We're not going to use the third contact column since our program has only 2 inputs. Press Select 3 times to insert a line and press OK. Wiring is probably the most confusing part of programming any programmable logic controller using the front panel regardless of manufacturer. Again, if you dork something up, you can always delete it and try again. We're now in the coil field. Press Select to insert a coil. Note the device inserts the default output coil Q1. Luckily, this is the one we want. Press OK to select Q1. The device inserts a Q1 and moves us to the end of the first and only rung. Note coil fields are also customizable, principally the coil function, the coil type, and coil number. If you wanted to, you can navigate left and right in the coil field and then scroll up or down among the various options. For our application, however, this simple program is complete. Press Escape. We'll return to the main menu. Before we place this PLC in run mode, let's take a look at our sample system again. Note our program only uses inputs 2 and 3 and output 1. Let's ignore the other devices and concentrate our attention only on these devices. Note the field input device attached to input 2 is normally closed by nature, despite it being instantiated in the PLC program as a make instruction. Remember, the electromechanical nature of a switch's deactivated state has absolutely nothing to do with how that input is logically instantiated in a PLC program. Recall that PLC programs require logical continuity, unlike traditional hardwire relay-based ladder logic that requires electrical continuity. In this case, our ladder logic program utilizes make functions for both input 2 and input 3 in series with one another to logically energize output coil Q1. Can you predict how this PLC program will respond to 4 different scenarios? 1. When both the red push button and the green push button are in their deactivated state. 2. When only the red push button is actuated. 3. When only the green push button is actuated. And finally 4. When both the red push button and green push button are actuated. By all means, pause the lecture and think about this. Here's a hint. What logical values do the red and green push button respectively send in their deactivated and activated states, and how do these logical values affect operation of the program? Let's run this program and see how the PLC responds to these 4 different scenarios. Navigate to Run and press OK to place the program in run mode. The device asks us to confirm our selection. Navigate to Yes and press OK. Press Escape to return to the home screen. When both buttons are in their deactivated state, the PLC indicates only input 2 is receiving a logical 1. No output coil is energized. When only the red push button is actuated, the PLC indicates no input is receiving a logical 1. No output coil is energized. When only the green push button is actuated, the PLC indicates both input 2 and input 3 are receiving a logical 1. Output coil Q1 is energized and the pilot lamp comes on. Note there's an audible click when the electromechanical relay Q1 closes. Finally, when both the red and green push button are simultaneously actuated, the PLC indicates only input 3 is receiving a logical 1. No output coil is energized. This behavior makes perfect sense. When no button is actuated, the normally closed red push button sends a logical 1 to input 2, and the normally open green push button sends a logical 0 to input 3. There is no logical continuity to energize output coil Q1, and the output remains de-energized. When only the red push button is actuated, the now open red push button sends a logical 0 to input 2, and the normally open green push button sends a logical 0 to input 3. There is no logical continuity to energize output coil Q1, and the output remains de-energized. When only the green push button is actuated, the normally closed red push button sends a logical 1 to input 2, and the now closed green push button sends a logical 1 to input 3. The program establishes logical continuity and energizes output coil Q1. The relay closes and the pilot lamp comes on. The relay, being electromechanical in nature, would exhibit a characteristic audible click when it closes. Finally, when both the red and green push button are actuated, the now open red push button sends a logical 0 to input 2, and the now closed green push button sends a logical 1 to input 3. There is no logical continuity to energize output coil Q1, and the output would remain de-energized. While in run mode, an operator can navigate to the ladder entry to monitor an existing program. Press Escape to enter the main menu. Navigate to Ladder and press OK. The ladder entry for a running program, rather than being a means of program entry, now shows the state of the inputs and outputs as manipulated by the operational program stored in memory. Notice when no button is being actuated, the ladder display shows input 2 is allowing logical continuity to input 3, symbolized by a highlighted bold rung. However, input 3 does not pass the logical connection onto the output. The output remains de-energized. When only the red push button is being actuated, the program shows no input is allowing logical continuity. The output remains de-energized. When only the green push button is being actuated, the program shows input 2 is allowing logical continuity to input 3, and input 3 is allowing logical continuity to the Q1 output, symbolized by a highlighted bold rung. The output is energized and the pilot lamp comes on. The output, being electromechanical in nature, would exhibit a characteristic audible click when it closes. When both the red and green push button are being actuated, the program shows input 2 is not allowing logical continuity to input 3. Input 3 passes on a whole lot of zeros to the Q1 output, and the output remains de-energized. Here's an actual PLC trainer performing this same program. We'll learn to make this inexpensive PLC trainer in a later application exercise. Note when no button is being actuated, the output remains de-energized and the first pilot lamp is unilluminated. When only the red push button is being actuated, the output remains de-energized and the first pilot lamp is unilluminated. When only the green push button is being actuated, the output is energized and the first pilot lamp is illuminated. When both the red and green push button are being actuated, the output remains de-energized and the first pilot lamp is unilluminated. If you consider yourself up to the task, I leave as an exercise to the viewer the following 2 challenges. Challenge 1. Given the system is wired as indicated, how would it respond if programmed using this ladder logic diagram for all possible combinations of input? Note this program, input 2 has been instantiated as a break instruction in series with input 3. Again, recall that the electromechanical nature of a switch's deactivated state has absolutely nothing to do with how that input is logically instantiated in a PLC program. Put your thinking cap on and figure out how the make and break functions respectively respond to the deactivated and activated state of the associated input devices. Think beyond colors. Red doesn't necessarily mean stop anymore. If you've got a PLC available, program it and see if your expectations match reality. Here's a quick hint. To change the logical operation of a contact from make to break in a program, press Select. Challenge 2. Given the system is wired as indicated, predict how it will respond if programmed in the following fashion for all possible combinations of input. Note for this implementation, input 2's make instruction is not in series with the make instruction of input 3, but rather in parallel. If you've got a PLC available, program it and see if your expectations match reality. Here's a quick programming hint. To add vertical wires to connect rungs, navigate to a horizontal wire and then press Select to change it to vertical. Delete deletes wires or devices that aren't needed. Alright, that about wraps up this brief introduction to the TECO SG2 10HRA PLR, just one of the many different types of basic programmable logic controllers commercially available. We familiarize ourselves with the layout and specifications of a TECO SG2 10HRA Programmable Logic Relay, and learn to navigate the menu and program it using the dedicated buttons, confusing proprietary keystrokes, and the ridiculously small LCD screen. We'll be taking a look at the much easier to use TECO SG2 client programming software to program this device in later lectures. Additionally, we learned to monitor the status of both inputs and outputs using the home screen, as well as monitor functionality of an operational program using the latter screen while in run mode. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.